Hello, explorers, and welcome to Reach the World's Explorer program. For 25 years, Reach the World has inspired youth to become curious, confident, and compassionate global citizens through virtual exchange. My name is Tim, and you have arrived at the third and final live event with the Tyrrhenian Continent Ocean Transition Expedition. Explorers Tessa and Larkin are joining us again today from the scientific drilling vessel JOIDES Resolution, which is still actually cruising off the coast of Italy in the Tyrrhenian Sea and continues to collect rock and sediment samples as it sort of approaches the end of the expedition this time around. We've already learned a lot about life aboard the JOIDES Resolution through the virtual exchange articles published on the expedition's homepage, and I'm going to share the link to that in the chat once we get started. And today we're going to have the dramatic and wonderful conclusion to the science lab tour that we started on board the ship on our last live program. We had so much to cover, and we're going to see some really interesting and fun things today. So stay tuned. We'll get started in just a minute here. Welcome to the teachers and students who are joining us live today or will be watching this recording a bit later. As always, our friends in Mr. Shvala's class at Palmer Public School. Hello, Honeydew Elementary, Kittredge Magnet in Atlanta. Hello to all of you. Thanks for being here. Thanks for watching the recording. I hope you had a great spring break. For those of you who are tuning in via YouTube, let us know you're here using the YouTube chat bar. Let us know where you're joining from. And of course, if you have any questions for Tessa or Larkin as we go, please drop them in the chat. We'll get to as many as we can in the next 45 minutes. We do have a lot to cover, though, in the labs today, and we are going to travel, without further ado, virtually to the Tyrrhenian Sea and connect with explorers Tessa and Larkin. So without further ado, hello.
Hello.
Tessa and Larkin, it's wonderful to see you. How are you?
Doing well. We are doing great. We are in week 7 of our 8-week expedition, and actually we're week 8 now. So we have 7 days left. So we are very excited, and we are excited to give you all the rest of the tour of this amazing vessel.
Yeah. So the last time, like Tim was saying, we were exploring the core lab, which is just where the main parts of the core come and where they come in their tubes. And so this is just our core lab. And so we walked through each of these areas, but there's more labs than just the core lab, and we wanted to show you those sections. So we're actually going to head down there like we would if we were coming from the core lab to them. So Larkin will guide us.
Yes, come right this
So
way.
let me switch my camera to her.
Is it on?
There it is.
Okay,
All right.
Perfect. All right, right this way. So we're heading down the stairwell, but on the way down, I wanted to show you all the pet wall. Now, this is something not scientific, but the scientists, when they're away from their families and their animals, they want to remember them. So they have all of these pets are from the different scientists. They put on their wall, and this is the pet wall. And then heading down this way, we have all of the logos from the different expeditions. And what's really cool about these is that each expedition votes on a different logo. So throughout each expedition, we are all there's a different theme. There's something going on that we're searching for, right? So all of these expeditions are all done by different scientists of that expedition. And then at the end of the expedition, we vote and then decide which logo that we have. So these are all different expeditions that we have done. We're going to keep on going down.
And so now we're on the foxhole. We immediately see the door to the geochemistry lab, and we'll walk right in. And the geochemistry lab is quite a useful lab because it gives us my minute, let me switch my camera here so I can face you all. Minute measurements, so like how much elements are in waters or minerals in the cores. So not a big core comes down here, just pieces of cores, kind of like powder parts of cores. So we do crush it up, and I have a geochemist that will walk us through what we are going to be looking through in the lab. So let me see. There's Emily in the back, so she tends to sit in the back of the lab. But let me go back to facing the lab so you can see we have all these sorts of bottles and different machines. My favorite is these pressers. So we're going to be walking through each of these machines shortly. The other thing is our geochemistry lab is shared with our microbiologist. So we do have microbiology research on the ship she likes to study life at the sea floor. So tell us what it is like to be a microbiologist on the ship.
It's complicated. It's complicated because most of microbiological samples need to be cleaned, and sometimes you need to work in a very clean space, and being a ship complicated things a lot because the source of contamination can be from everywhere because there is microbes everywhere, and the microbes communities are unique from different sides, from the air, from the water, from the soil, from sediment, from different places, and we need to try to keep everything sterile, try to keep the contamination as far as possible in order to have good samples that can be significant for microbiological research. In general, we use different tools. Example of an autoclave. This is it's like a pot that keeps all the materials inside. Can be I don't know what is the word. Well, we apply pressure and heat, a very high pressure, a very high heat that it allow us to kill everything before use any tool that we want, regardless if it is a syringe, or if it's a spatula, or anything that we wanted to use. So we guarantee that we have a sterile, no microbial contamination from other sources, instruments or tools for use that.
And what do you want to look for when you take samples?
I'm taking samples from the sediment. So study the microbial communities of these sediments, in this case of the Tyrrhenian sediments, to see how deep the life can go and what are the communities that live there. Because they are amazing microbes. They live in dark conditions, high pressure, in the cold. They are very extreme. They are the ancient earliest organisms in the story of the Earth. They were here before us. They're going to be here after us, probably. That's incredible how they just adapted to all the conditions, and they are everywhere. With oxygen, without oxygen, with light, without light. It's amazing.
That's awesome. And then, do you get to study them on board, or do you have to take them somewhere else?
No, I cannot study them on board. It's complicated. I know that some people try to make DNA extraction here, and it didn't work. So what we do is just take the cores and freeze the cores for rounds or syringes. We freeze them at minus 80 degrees Celsius, so we can keep them in a latent state, like very frozen, and then we just unfreeze this on shore, and we can get DNA from the sediments.
Great.
Really complicated, but it works.
And knowing the DNA will help you do what?
It helps me to identify what are the communities, and not only identify microbes, but also identify other organisms, non-living creatures like viruses. Not only to say, there is this microbe A, B, C, community A, B, C, but also to know functional roles. What are the functions? What are the main roles into the ecosystem? Because microbes are like the cleaners. They are like the worms in the soil, but they are in the ocean. They keep our ecosystem balance. Yeah, they keep our ecosystem balance and becoming the nutrients available for other organisms.
Great. Tim, are there any questions before I move on to the geochemist?
I do have a question. Hello. First of all, we didn't get a chance to get your name. Can you tell us who you are and what your job is and where you're from?
Sure. I'm Milena. I'm the microbiologist on the ship. I'm a PhD student in Texas A&M University, but I'm from Peru.
All right. Well, thank you so much for sharing your work with us today. For students who are watching, when you say microbiology, you're saying you're looking for like things you can't see with the normal eye. And it's for perhaps a non-microbiologist, it's hard to imagine that as you're drilling really deeply into the seabed, that there could be anything living down there. How far down, when you pull up a core sample from way, way beneath the seabed, there are living things within that sediment and rock?
Of course, there are even living things in the rocks. Well, my research is not focused on the rocks. I'm not taking any rock samples, but I have some colleague in a past expedition that she took rock samples. Yeah, she found life there. Because the life span extended meters and meters, I mean kilometers below the sea floor.
That
We
is
don't know why it's
amazing.
living. Yeah, it's amazing.
So, and if I understood you correctly, you're processing the samples that you're collecting on this expedition. You'll take them back and look at them more closely for things like DNA or other characteristics back in the laboratory at Texas A&M?
Yes, in Texas A&M in Galveston. So we are taking DNA from 16S RNA gene sequencing to look into the bacterial and microbial communities in general, and also we are taking viral metagenomics from sediments.
And do you, at this point, do you know whether you found anything, or do you have to wait till you get back to the United States to figure out if there's anything that you're looking for in the samples you collected?
Yeah, I was targeting to look especially sulfate reducers, that kind of group of bacteria that helps in the reduction of sulfur compounds. But I hope I can get some. I also started some enrichment cultures to try to isolate them. Some of them are working, some of them are not working yet because it's been just a short time. I may probably need some months. But for now, I just don't know what I'm going to find. Hopefully.
Exciting.
Yeah.
The discovery continues long after you leave the JOIDES Resolution. Then thank you so much for sharing your work with us.
Sure.
Great. So Milena shares an office in the geochemistry lab with one of our geochemists, Emily. And Emily will talk to us a little bit about how you can use the lab for your research.
Yeah, so I guess I'll give you kind of a general overview of the geochemistry equipment that we have on board first. So we do a lot of different types of geochemistry. So we do primarily, we collect sediments and we collect hard rocks. But there's multiple different kinds of samples we can run. So the first thing that we do when we're drilling sediments is whenever a core comes up, they'll get one whole round of the core, like just a slice of the whole core. And then they put it in this apparatus that squeezes the water out. And so you can attach a syringe here to collect that water. And then the sediment, I'm an igneous geochemist, so I study the rocks, the hard rocks that we get. But the sediment geochemists will then take that water and they will analyze it for salinity, for which they use this little handheld guy, which is really cool. And they measure it in this instrument for alkalinity. They measure for phosphates with that instrument over there, and then they can measure total dissolved ions with this instrument right here. So just free elements that are sort of floating around. Another really interesting thing that they do is they take a very small core of, they take a very small core, I can't find their little thing, but anyway, so a core about this long and about this big in diameter from the actual sediment cores that come up. They put that in a glass vial, so it ends up looking like this. So this is sort of that material. They come back, they put it in the oven, they heat it up for about 30 minutes, and then they insert a syringe into the top of that vial that's sealed. They pull some of the gas out, and then they insert the gas directly into this instrument, which is called it does gas chromatography. So it basically tells us what's in the gas. And this was actually just really helpful because we just drilled some halite, which is rock salt. And rock salt is a really good, what we call a trap for petroleum products. So like natural gas and stuff like that, because halite is not porous at all. The gas can come up beneath it, but it can't move through it. But our ship is not designed to drill in any sort of pressurized systems. So anything where there might be hydrocarbons, which are hydrocarbon is like the umbrella term for petroleum and natural gas and stuff like that. We can't drill into it. So the sediment geochemists were the ones that were like, hey, we need to stop right now. This could be getting dangerous. So this was actually just extremely relevant and very helpful. And it always is, but on a very fast time scale, they were just able to get results that really helped us out. What I do specifically, this is where one of the few places that igneous and sediment geochemistry really cross over, is we both use this instrument, which is called it's ICP AES. It's a kind of a complicated acronym, but it tells us what is in basically the bulk chemical makeup of fluids. And so the sediment geochemists can take their pore water, which is when they get the water out of the sediment, when they squeeze it and the water comes out, that's called pore water. So they can take that pore water, they dilute it with acid, and then they can measure what it's made of, basically, what all of the elements that, all of the element abundances in that water in this instrument. And igneous geochemists like myself also use this instrument, but I said we have to use it on liquids, so that's where it gets a little bit complicated. So we take our samples, we have to grind them on all sides, make sure they're really clean and there's no like foreign material. We wash them, we then powder them, and then they have to sit in an oven at over 1,000 degrees Celsius for 24 hours to make sure that we get all of the anything that shouldn't be in there, that wouldn't have originally been in there when the rocks were molten, comes out in the form of gas. And then they take that powder and we make it into a glass bead. So we fuse it with another material called a flux.
And wait, hold on. So Tim, I gave you a photo of that. So do you want to share that on the screen? So one more. There you go.
Cool. Yes. So this is what the glass bead, this is like the formation of the glass bead. So you can see that there's lots of little droplets. And so this is sort of at this stage, this is like early stage glass bead formation. And then right after this stage, the machine actually starts to oscillate, and it sort of like swirls all the beads together. And then that's shortly after you take it off. This whole process only takes like 3 minutes. It's really incredible.
And then Tim, if you go to the next picture, there you go.
Yes, so that is a glass bead. So then once we have those glass beads, that's still not a liquid. So we have to dissolve it then in acid. And then when we dissolve it in acid, it gets put into these little jars. They're not really jars, but bottles in there. And then right before we analyze it, we dilute it a second time. So it ends up being about only, it's like a 1 to 5,000 ratio of like 1 part of the actual solution and 5,000 parts of what we dilute it with. And then we can measure it in the ICP. So that tells us what the rocks are actually made of and can really help us identify what types of rocks we are actually getting. So we can look at them and that tells us some things, but really the bulk geochemical analysis is what actually defines the rock type.
Nice. Tim, any questions for my geochemist?
I have so many questions. Hi, Emily. It's really nice to meet you. That was fascinating. It really helps me and our students understand what is keeping you really busy and has kept you busy over the last, 2 months or so that you've been working on this. How do you, knowing how much rock that is coming up from the seabed through the drill, how do you identify what you do all those processes to and what you are like not that interested in?
Sure. So the first step is, the first step in the description process is with the petrologists. You guys talk to the petrologists? Yeah, so the petrologists do the first step. They identify the minerals, and then we also do a little bit to help them there. Sometimes they get a little bit stuck, and so we have another geochemistry instrument that we can use upstairs in the core lab that's called the PXRF. And it's really cool because it can do spot analysis and give you bulk rock geochemistry, but it can do that in like 2 minutes, which is incredible. But the downside is that the data are pretty poor quality. So it's really helpful for like qualitative, like, okay, we think this rock is probably almost 40% magnesium oxide, but it's not really good for like hard, like this is this type of rock. It's just good for general analysis. So we help them a little bit up there whenever they get stumped or they're not sure what something is. But they do the general analysis, and they are usually spot on with what rock type they think it is. We maybe out of 20 or 30 samples that we run in the ICP, we usually only have to change the rock type of like 2 or 3 of them based on the bulk geochemistry. So they are really dialed in and they're really great. What they describe all the core first, and then once a day, whenever we're drilling hard rock, all of the cores that are split and described get laid out. And then we get to go through with the whole team, the whole hard rock team. So like, really the petrology and geochemistry team. And we decide where we want to do bulk rock geochemical analysis, usually all together. And so we can target, if we have like long sections of core, like multiple sections of core that are all the same type of rock, we may only take 1 or 2 samples. But if we have a lot of different types of rocks, we have a lot of different veins or a lot of really interesting features, or if they're just like texture or color differences and we're like, that's weird, we don't know why that's like that, then we'll take samples like that. So usually it varies between like 2 to like 4, maybe 5 per. It's uncommon to have 5 per like section of core, like 1 meter core, but we have had up to probably 3 or 4 per 1 meter section.
Okay, so you can have a lot of variety of rock in one rock core sample that comes up. Fascinating. My only other question before I turn things back over to Tessa is, how does somebody become an igneous geochemist? What is the career path to that career field?
Sure. So igneous geochemists, really, so there's 2 different types of igneous geochemistry, there's different types of geochemistry, but for igneous geochemistry, usually we are petrologists. Like most people start as petrologists. I consider myself more of an experimental petrologist, and so that means that I do a lot of experiments in the lab, like high pressure, high temperature experiments, and so I'm technically a petrologist, but experimental petrologists especially are really like geochemists. So like we mostly do geochemistry, but so yeah, I have an undergraduate degree in geology, and then I got a master's degree in pretty much straight up petrology. And then when I started my PhD, I'm a PhD student, I'm in the later years of my PhD now. I switched to experimental petrology, which has me doing a lot more geochemistry, but really geochemistry and petrology go like very much hand in hand. But yeah, so I guess, does that answer your question, or was there something more specific?
No, it does. Were you really into rocks as a kid? Like, does this start from, you had like an awesome rock collection?
Oh, well, yeah. So I grew up in Appalachia, so like East Tennessee, like super rural. I was just like running around the woods like a feral child most of my childhood, and asking my dad questions about the rocks. Like, did these fall out of the sky? Where did these come from? And he's like, I have no idea. Go ask your mom. Yeah, I always did like rocks, but I sort of came to geology kind of late because I had not a great science background in high school. So it wasn't until I got to college that I realized that science was something that I liked and could be good at through really wonderful teachers, luckily. So yeah, I didn't declare my geology major until the summer after my second year. So I guess the moral there is there's always time to get into geology if it's something that interests you.
Wonderful. I think that will really appeal to a lot of kids who love rocks and are curious about what they are. And Emily's a great example. If you really want to find out what they are, there you go. There's the path.
Take a geology class. Yeah, it's fun.
Yes. Excellent. Very nice to meet you, Emily. Thank you.
Yeah, thanks. Nice to meet you too.
Thank you, Emily. We're going to go out that way. All right. Thank you. Have a good day.
Thanks.
All right. So Tim, next is when you actually get to hard rock and when you want to look at more hard rocks. I have my marine technician who is the thin section specialist. So we kind of touched upon thin sections, but Max will walk us through what thin sections are, how he makes them, and then how he knows to make them. So Max, take it away.
All right, how we doing, folks? So what I do in this lab, I take rocks, big rocks like this, and we turn them into something like this. We make it so thin that you can see right through it.
Let's tilt it up a little bit.
This way?
This way.
This way.
Just to show that it's like pretty. Yeah. Perfect. Okay.
So, how do we do that? Let's start out with, why do we do that? Why would we bother? Well, the simple reason is, when you look at this, I mean, you can kind of see what's in it, but you don't really know exactly, right? I mean, there's a mineral, okay, that's yellow, that's like tan, that's white, but sometimes you can't really identify them just by how they look. So what do? We take it, make them very thin, we put them under the microscope, and then the way that the light interacts with the mineral with a couple filters, we're able to identify what those minerals are. So that is why we do it. Now, how do we do it? Very simple. We take the rock and we cut it flat. So in this one, we took it on a big saw and cut it flat so there's no bumpy spots. Now, it is on a big spinning saw. That saw is going to be speeding up, slowing down, and it's going to vibrate a little bit. It's mostly flat, but we need really flat. So what we do is we then take it and we bring it either to this machine or to this piece of glass. But we're going to stick with this machine for now. So what this machine does is it's a turntable. So if I click this button, it spins. And we also have water to help keep everything cool and make sure that we're removing all the material that's being cut off. And this is a sandpaper disc. So we have a bunch of these discs, all with different hardnesses and coarsenesses, so we can make it finer and finer. So when we first get a rock, it's actually surprisingly bumpy, maybe a millimeter or half a millimeter in bumpiness, which half a millimeter isn't much, but we need it way smoother than that. So we put it on this one, which is the coarsest sandpaper we have. And that gets it pretty close, but now we've got scratches and, well, it doesn't look very nice. So we put on the next one, and the scratches get smaller and shallower, and then again further and further until we get it as far as we are going to take it. Now, we've got a rock that's beautiful, but it's really shiny. And you would think, well, that's perfect. That's exactly what we want. We want shiny and reflective. Yes, but actually no. To observe it, yes, we want it shiny. But now we got to take it and stick it to a piece of glass. So back here, I've got some slides, and these are just microscope slides. But if you, I don't know if you can see it under the light, this side on top is kind of reflective and shiny. But if I flip it over, this side is dull. It still catches the light, but it's not photoreflective. So the reason we do that is to make some surface area for the glue to attach to. Because otherwise, if you try to bond two pieces of glass together, there's just nothing for them to hold on to. So we take the rock and we put it onto this. This is carbide grit. It is usually the same coarseness as our discs, but since it's more irregular, it scuffs it up into a nice uniform pattern. So then we take the rock and we glue it onto the glass like this. So this is one that we were doing for fun. And we have a nice piece of rock here, and there's our glass glued onto it, and we let that cure and sit. So once that glue is done, we're going to move on to our next machine. Follow me this way. So this machine right here has a cutoff wheel, which is a regular quote-unquote blade. It's a diamond wheel. So this is actually not sharp in the conventional sense, but it's very hard, and it abrades and just wears the rock until there's just nothing left. It just wears away. It's basically a glorified tile saw. So what we'll do is we'll take this and attach it to this face right here. Now this groove that's in here, we apply a vacuum, and that's what keeps this stuck to it. So it's adhered nice and good. So here's another sample that'll actually fit.
Oh, it looks like we lost our signal real briefly from the ship. I'm sure that they will come back.
Oh, are you still there?
Yep, they're back. I was just vamping a bit, and I'll turn it back over.
Okay, go ahead.
All right, so this is one sample that we've already stuck to the glass and prepared, and partially cut it. I don't know if we see that.
Yeah,
all right.
I can see what you're saying.
So we take that, we put it back on here, and then we move this to the left and drop it down. And so what we would do is that would cut off most of the rock, but not all of it. Now, it does mean that the part that is still stuck to the glass is still kind of thick. It's just under a millimeter thick, which again is pretty thin when you think about how thick is this rock. It's way too thick when it comes to, let's put it under a microscope and shine light through it. So the next step is this grinding cup over here. So what we do is we then, because this is articulated, put it down, and we just let it ride right up against it, and that'll grind it away slowly. And since it's a lot thicker, it's more rigid, it doesn't vibrate and flex as much, it gives you a more consistent reduction in thickness, especially we have this micrometer here. And this number helps us tune in exactly how much material we're removing every time. So this entire wheel will actually move.
All right. Do you want to show an example, show the video of the light moving through it?
Yeah.
So once we put the final thin section, so once this rock is completely thin, we can run light through it. And if you move the microscope slide across the light, you'll start seeing light move through it at different ways. So all that light sort of flashing is the light moving through the different grains that exist in the thin section. And this tells the scientists different pressures and temperature that the grain underwent. And this gives them a better idea of what happened to the rock in the bigger picture tectonic plate. Any questions, Tim?
Yes. Hello, Max. Hey, I'm Tim. That last image that we just saw just strikes me as kind of beautiful. I mean, it's kind of mesmerizing. It's like a computer screensaver, or it's just remarkable. Is the amount of variation in the sample that you just showed us typical for a certain kind of rock? Like, if you look at that, would you say, this is very, very common or unusual, what we were looking at just then?
I don't think you can say it's common or uncommon. There are many rocks that are like this that have kind of homogeneous numbers and sizes of grains, but I actually have a different mineral
Let me show a different one.
That is completely different.
Oh, yeah.
Are you seeing it, Tim?
Yes. Yeah.
So each of these grains show you a history of like what grew through the matrix of the rock. So a lot of the petrologists use these microscopic images to understand what is in the rock, what happened to the rock, like what's its story. And like I said, like how much pressure was applied to it, how much temperature was applied to it, and what changed. Because sometimes they can look at this grain and be like, oh, this grain should be like a square, but now it's really long. That tells me it got compressed or something. So like Max is saying, it's not necessarily common, but the features that we look for are common. How much light goes through it? Does the light change its color as we move the slide across the table? And then what's its shape? And is there any like other features that they can observe, like scratches or stretching?
Okay, I have two more questions about making the thin sections. Is it common when you pull up a core to get a big rock? Like you showed us a big rock as an example, or are you sometimes processing just little bits of rock that came up in the core?
So that was a piece of rock that we got from one of the countries that we visited just to practice, and especially for other tours, just to kind of, big rock becomes very thin. Usually the core is about that big. I can actually show you guys the size of some of the samples that we have to work with.
Let me switch my camera.
So like this is one of the samples that we're currently working on. This is encased in epoxy just because it's so soft, but that's not very big at all.
And then there's even these.
Yep, those are some of the billets. Those are a little bit larger, but anywhere between that one and this one would be a good amount. Any smaller and it becomes pretty difficult to mechanically hold it while you're working, but I'd say that's pretty typical. Those are unusual. These sizes are.
And before you know exactly what kind of rock you're working with, are some rocks harder or softer and therefore easier to make thin sections from?
Absolutely. So things that are hard, like a granite, are, I won't say more difficult to work with. They're just different. On a granite, you're going to be pushing down and just letting it grind away as much as you can, as quickly as you can. And even then, it'll take a while. On the other hand, things like a shale or a sandstone is so soft. You barely touch it and it's already washing away. So you definitely have to change your approach to the different rocks and conditions that the rocks arrive in. Sometimes when they're damp, they hold together really nice, but then you dry them out and they crumble and fall apart into dust. So it's horses for courses.
So the petrologists basically identify the pieces of the rock after they describe and did what Emily was talking about, like looking through the samples, and then they'll tell Max, okay, I want this part of this core or this part of this core, and then let him know about the types of rock to expect.
Okay, great. And on average, how long does it take you to make one thin section from a rock sample, and the average sort of rock sample?
A lot of the time is just how long it takes the glue to dry. But if I had 8 or 12 hours, I could make at least one sample. But the general expectation on the ship is 8 thin sections for every 12-hour shift. but that is with the understanding that you have an assembly line going. Once you're done one, you glue it, move on to the next one, and in theory, that's how many we should be getting done.
And are you, and I know at some point you have to sleep on the ship. I hope you sleep. That someone comes and you sort of bring them up to speed on where you're leaving off, and they take over for a period while you sleep,
So,
or
most labs are like that. The thin section lab is generally not. There's only one thin section tech, and that's me. But in the chem lab and other labs that do more volume, do have two technicians who will trade off responsibility.
All right. Well, thank you for showing us your process and telling us about thin sections. Appreciate it.
Of course.
Fantastic.
And then one more lab, Tim, or the one thing to show, which is the XRD lab. So Kristen, sorry, we got a little delayed, but Kristen will tell us about the XRD lab.
So the XRD it's where we learn about the fingerprint of a mineral. Every mineral has its own unique fingerprint, and we're going to find that out in here with these machines. But when a sample comes in here, the first thing that you're going to do is we have to powder a sample. So whether it's a hard rock or mud, like from a rainy day, or compacted sediment, you've got to turn it into a powder. And so we would use, on the mud, we would dry it out and we would crush it using a mortar and pestle that you might find in your kitchen at home. But if it was a hard rock sample, you would probably take this and cut it into 5 or 6 different pieces. And then we would put it inside of one of these. And this puck, we call it a puck. It's a tungsten puck and probably weighs 4 or 5 pounds. Goes inside here with all the little shards of rock. And you would put the lid on it and take it into another room over here that has a shatter box, and it shakes it violently. And when it's all done for 10 minutes or so, it's going to turn it into a powder. So this would turn into this. And so now we have a really, really fine powder. And as you can see, the powders can be all sorts of colors depending upon what's in the core. And so this is where the scientists may look at the core upstairs and sort of guess at what's in the core of the minerals, but they're not going to know for sure until it comes here. So we would put this powder in a sample holder, and then over here, the powder would get put in here, and then these are some samples that are ready to run or have maybe run already. I'm not positive, but I can show you over here on this machine. We have 2 X-ray diffractometers. So basically how this machine works is we would have this sample filled with the powder that we just made. And inside here, it's all sealed up and shielded, but we've got an X-ray tube here. We've got the sample sitting inside here, and there's a detector over here. So we know that the X-rays are hitting at a known angle, and depending upon what minerals are in here, they're going to bounce back up at a shallow angle, a steep angle, somewhere in the middle. And so this machine's then going to give us data like this. And so this is the known fingerprint for copper. So we know that copper has a huge peak at 32 degrees and sort of a medium-sized peak at about 45, and some other smaller little peaks. Whereas the mineral like calcite has a really tall peak at 29 degrees. And where it gets interesting is where if you overlaid these 2 graphs, then the scientists are left to decide, once you've looked at these long enough, if you see a peak at 32 or 45, you're sort of like, oh, I know, that's definitely copper in there. But some of our samples have 4 or 5 different minerals in them. Gypsum has its own fingerprint, and everybody has its own fingerprint. And that's where the scientists come in, and we have databases where they can run through, and the software will tell you, we think it's got gypsum and pyrite and copper, calcite maybe, and that's how we know for sure what minerals are actually in samples.
Great. Tim, any questions?
I always have questions, Tessa. You know I do.
I know.
Kristen, it's so nice to meet you. That's such an interesting process. My first reaction is I have a whole bunch of things I would love to put in a shatter box and see what happens to them.
You can pretty much powder anything. Billet powder.
It seems like a pretty fun tool as lab tools go, to take something that sometimes may seem like it's a rock. It's not, it can't get any smaller. It's a rock. And to be able to reduce it to powder like that is really interesting. You said that you are looking at the fingerprint of a rock. Now, when we're talking about rocks, is it common to find lots of different minerals within a rock?
Usually, yes. You usually very rarely find pure calcite or quartz or dolomite or whatever. Usually when you've got a sample, this big, you can have 5 or 6 different minerals in it.
Mm-hmm. All right. And do you sometimes sort of, you see a rock sample and you kind of like, oh, by color or by weight, it kind of, I'm guessing it could be this, and then are completely surprised by the results?
Definitely. The scientists are definitely sometimes surprised because they can be upstairs in the core lab and go, this is definitely dolomite, definitely. And then we come down here and we run it, and 12 hours later, it's sort of like, actually, that was not. That was quartz. But, they look the same to the eye, but when it comes to this fingerprint, it can be something very different. Scientists aren't wrong that often, but sometimes we surprise them with this information.
Is this the primary method for determining as definitively as you can what the minerals are within a rock sample? Or can you take it even further? Is there something where you're like, you described at the end, like we're pretty sure, very sure it's this. Is there like one other thing you can do to make it 100% sure? Is this the process?
I think this is the process. I don't know that there's one more step to for sure know the mineralogy of a sample, but because that's what, with all the databases of all the, exactly, we know what copper looks like, this, and this. This is sort of the end of the line. Kristen, correct me if I'm wrong, but we do many steps, right? Like we do the ICP, and then we do the PXRF, like we yes complement the measurements. Definitely, we complement them, but we're all sort of making sure that they're all lining up. Yes, we're lining up the same.
Okay, and then
but we talk about the beads in the geochemistry lab, so all good.
And so you're identifying the rock through all these different ways, and they will probably, if you're right, sort of come together in the middle at some point and be like, yes, confirmed. The clues you're getting from lots of processes are all pointing in the same direction.
Definitely. When those scientists all meet together and come up with all the different results they've gotten over the past 24, 48 hours, they all hopefully point to the same thing.
All right. And can you tell us, before we let you go, how you got into this kind of work? What's your career path? How did you become interested in this?
So I'm a little bit different in terms of I was working at Texas A&M, and my major was in biology. But as a college student, I got a job at IODP, and I stayed, and they needed somebody to sail. And I was sort of like, yes, I can go sail on a ship halfway around the world. And but most people out here definitely have geology backgrounds. Everything I've learned about geology has been from being on this boat, but I've had to learn it sort of quick and fast.
And how many JOIDES expeditions have you been a part of?
25 or 30, 25. Something like that.
Wow.
I'm jealous.
What's your favorite thing about working and living on a ship? Because you clearly keep coming back to do it.
I do keep coming back. The people, it's sort of like, it's a family out here, and you have your family at home, but when you're sailing every other 2 months for all year, I mean, you're almost sort of here more than you're traveling and being here more than you are at home. So they're sort of like your second family, and when grandkids' birthdays are and all those things, and did your daughter graduate and things like that, and you check in with your ship family.
Yeah, Amazing. Well, it's really nice to meet you. Thank you for showing us your work. It's fascinating.
Thank you for having me.
All right. Thank you, Kristen.
You're welcome. Kristen is awesome.
All right. So those are all the additional labs I wanted to walk us through. Are there any last questions you wanted to cover, Tim?
That is amazing, Tessa and Larkin. Thank you so much for introducing us to those interesting people doing all of these interesting things. I had sort of assumed that a lot of the samples that were being collected needed to go off the ship to be really processed and, you know, learned about. And the beginning of deciphering these clues from the seabed happened, you know, off the ship in the years that followed. And I can tell from today alone that so much of that processing and analysis can happen on the ship, which is really kind of amazing.
Yeah, there's an extensive amount of shipboard analyses, mainly because the more the samples and cores are left out of the sea floor, the more it can change and react, just like how seawater can make metal and like the ship start rusting. So for instance, the pore water that Emily walked us through, they can't touch a sediment core 2 days after it comes out of the seafloor for pore water. It's not worth their time. They literally come get the section from the core deck and throw it into the squeezer and preserve that water because it will start reacting with our oxygen, our pressure, our temperature. So a lot of analyses have to happen ASAP.
Wow. Well, that's it for me for science-related questions. Before we let you go, though, I know both of you are getting towards the end of this expedition, and you've been at sea for a while, and it's been so much fun to follow the expedition and to sort of see this experience through your eyes and learn so much from you like we have. I just wanted to ask you, like, what you expect from the next couple days as the expedition winds down. What are you going to be doing, you know, science aside, to wrap up this expedition and be ready to be back on dry land?
Sure. So for me, I'm going to be wrapping up some of the projects that I started out with. There was a lot of video projects and interviewing people and just making sure that everything gets wrapped up. Just gearing up for home. What about you, Tessa?
Yeah, pretty much the same. So for outreach officers, we come on board with sort of a set number of projects, usually like one or two bigger projects outside of social media and like the typical like doing broadcasts daily. So kind of finishing those up, and then also just checking in with the scientists and seeing where they are and just kind of knowing what the next steps are for them. Because I know we are both interested in trying to follow the scientists through their time because they have about 4 more years of work with these expedition data. So I think we're both curious to see what happens after.
Yeah, one of the things they did was they did a presentation on different places that we're going to be meeting up in a year from now to get back together and to compare notes and things. So that's interesting too. That's another thing that we'll be following up on next year.
Okay. Well, it's fun for us to know that the project continues long after the ship comes back into the harbor, and that all of these like clues, these samples from the seabed are going to go probably different corners of the earth. I know you said there's a depository in Texas. And there's also one in Germany and Japan. And then in a year or so, as Tessa said, some of the group is going to get back together. And at that point, do you talk about like what has been discovered in the year that's gone by?
It's so easy for scientists to get together and talk about what their findings are in real time here on the ship because they're in the lab next door. But when everybody is in different parts of the world, it's going to be a little bit more difficult to set up those kinds of meetings. And so when that meetup comes up again, people can compare notes and come with some answers.
All right.
Yeah.
Very good. Well, I thank you both so much. It has been so fascinating to travel virtually and learn from you both. You have worked tirelessly to show us all of the incredible things happening aboard the JOIDES Resolution. And I know we're getting towards the end of our virtual exchange articles as well. So I put in the chat the link to Tessa and Larkin's virtual exchange homepage at reachtheworld.org. Make sure you check out their articles, especially if you want to go back and sort of like review some of those things that like we touched on briefly in these laboratory tours, and maybe hear or like see the words in print if you want to look it up and learn a little bit more about any aspect of that process. This has been such a great learning journey. Thank you both so much. For our students and teachers who have been following us, thanks so much for following. We do have at least one article to go still. At least I think it's a farewell article from Tessa and Larkin as they wind things down aboard the ship. So maybe we'll get to see a picture of you with the joy in your face when you're back in Italy and eating some fresh pasta and recovering from this great adventure. But thank you both so much. For now, I'm going to say so long to our audience today. Keep exploring the world around you. We will, I'm sure, come back to the JOIDES Resolution again at some point to go on another adventure with them. But for now, that is it for the live portion of our Tyrrhenian Continent Ocean Transition Expedition. It's not the last time I'll have to say that expedition name, but I get better every time I say it. So Tessa and Larkin, thank you so much. It's great to see you. What a wonderful tour today.
Bye. Thank you for joining.
Thank you.
Bye.